In course of this video we will learn how to use digital multimeters. The resistance of miscellaneous devices will be determined directly as well as indirectly by measuring voltage and current. Some remarks about the quality of the used instruments will follow at the end of the video. There are 3 plug-in connectors at the front side of the multimeter. The black test lead has to be connected to the middle connector and the red test lead to the right one. Only while doing current measurements above 200mA, the red test lead has to be connected to the left connector. For those measurements, the shunt is used, which is the wire strap at the bottom right of the board. At the mid-bottom you can see the 250mA fuse. Below the board you can see a 9V battery used for internal power supply of the control electronics. While using the direct method of resistance measurement, the jacks of the multimeter are connected to the internal battery. The current running through the test device depends on the voltage output, and those variables are scaled to a resistance value. First I will attach a potentiometer to the clamps of the multimeter. Even while adjusted to the maximum value, the measured resistance is just 846 kΩ, which is clearly below the printed value of 1 megaohm. Let's discover the resistance of some carbon film resistors now. A pattern of colored stripes indicates the resistance and the tolerance of the resistor. For the 220 kΩ resistor we get a measured value of 0.218 megaohm, which is 218 kΩ. We get 27 kΩ for the resistor, which should have 27 kΩ. I can switch the multimeter to a lower range while attaching a 2.7 kΩ resistor, and we get exactly 2.70 kΩ. While switching to the 2 kΩ range, a single 1 is displayed, indicating that the measured value is too large for the used range. We get 389 ohm for the 390 ohm resistor, and 10.7 ohm for the 10 ohm resistor. The last device is a piece of wire with a diameter of 1mm and a length of approximately 4 cm between the 2 clamps. We get 0.8 ohm, which is very high for this piece of wire. Let's connect both clamps of the multimeter. We should expect a value of 0 ohm, but what we get is 0.7 ohm. One reason for this curious value is the transition resistance of the clamps and cabling. Another one is the low precision of the multimeter while measuring devices with a low resistance. With the help of a second multimeter at the right side, we can detect the value of the voltage output of the left multimeter while doing resistance measurement. Let's use the potentiometer as an adjustable resistor. The voltage output is between 0.25 and 0 volts, depending on the adjusted value of the potentiometer, and the negative terminal is at the black cable. The voltage output and the polarity are not standardized and can be different at other models. The displayed resistance value of the potentiometer is curious. While the second multimeter is connected in parallel to the first one, the value is just 457 kΩ, in comparison to 846 kΩ without this instrument used for voltage measurement. Effectively, there is another resistor connected in parallel to the potentiometer by attaching the second multimeter. More about this will follow some later in this video. Let's do some indirect resistance measurements. The resistor is connected to an adjustable DC voltage source with a maximal output of approximately 10V, which is non-hazardous for human life. The very simple control electronic consists of a single PNP transistor with a potentiometer connected to the base pin. Another video will show how to build better adjustable voltage sources. Be careful while doing measurements with multimeters. Like mentioned before, the test circuit will only be attached to low voltages. Never touch uninsulated wires or devices at unknown circuits while they are attached to a voltage source. While doing measurements with the help of a multimeter, be sure to switch the device to the correct function before attaching it to the live circuit. Don't switch between different functions while the multimeter is connected to the circuit under test. What happens if the multimeter, which is connected in parallel to the resistor for doing voltage measurement, is switched to current measurement by a mistake? Well, the internal resistance is very low while switched to current measurement, hence the resistor connected in parallel to the multimeter gets bypassed and a high current is running through the circuit and the multimeter. This may cause the damage of devices. In this case, the transistor used to adjust the voltage output could be damaged. To avoid the damage of the transistor, I have installed another resistor in the test circuit, which is the weak point of the system. As you can see, those resistor is heating up strongly and gets destroyed. So always adjust the multimeter to the correct function before starting the measurement at a live circuit. The multimeter has to be switched to the functionality DC voltage to be able to measure the voltage drop at the resistor. Set the range selector to the highest position if the value scale to be measured is unknown beforehand. Now you can connect the multimeter in parallel to the resistor with the help of the test leads. As you can see, the clamps are bare, which is why they should definitely not be used while the test circuit is connected to high voltages. When doing voltage measurements, you may switch between different ranges while the multimeter is connected to a live circuit. But watch out! Don't change the functionality while turning the switch. If the selected range is too small for the measured value, a single one is displayed again. A minus sign is displayed if the multimeter is connected with wrong polarity, meaning the more negative terminal is connected to the red cable. The multimeter has to be connected in series to be able to detect the current running through the whole test circuit or a single device. I am opening the circuit at the negative terminal to insert the multimeter. Now I am switching on the power supply and we can read a value of 4.5 mA. When doing current measurements, the power supply should be turned off while switching to another range. The current running through the multimeter is interrupted for a short span of time whenever the switch is turned to another range, which may cause dangerous voltage peaks if inductors are inside of the test circuit. The lower range allows a more precise measurement and a value of 4.52 mA can be read. A minus sign is displayed if the multimeter is connected with wrong polarity. We get a value of minus 4.53 mA. With the help of two multimeters, the current running through a resistor and the voltage drop at this device can be detected simultaneously. The multimeter used for voltage measurement, which is called voltmeter, is connected in parallel to the resistor. The multimeter used for current measurement, which is called ampermeter, is connected in series to the parallel circuit of the resistor and the voltmeter. With the help of this arrangement, we can analyze the resistance of several devices while exposed to different voltages. This arrangement of the two multimeters leads to considerable deviations while determining devices with a high resistance. The inner impedance of the voltmeter is high but not infinite. Consequently, an additional current is running through the voltmeter, which is detected by the ampermeter too. We can check those current with a third multimeter. This one is switched to current measurement and connected in series to the voltmeter. Instrument number 1 and number 3 are connected in series to each other, but in parallel to the resistor, and instrument number 2 is connected in series to those branches of the circuit. Multimeter number 3 displays the current which is bypassing the resistor, and we can subtract those values from the current value displayed by multimeter number 2. Hence, the resistance is detected more precise. While using the 1 megaohm potentiometer, a current of 0.012 mA is running through the voltmeter. This value has to be subtracted from the 0.022 mA displayed by multimeter number 2. The leakage current is approximately half of the total current. This ratio is decreasing the lower the resistance of the tested device becomes. While using the 390 ohm resistor, those leakage current can be neglected. If there are just two multimeters available, you can use another circuit. The ampermeter is still in series to the resistor, but the voltmeter is by now connected in parallel to both devices. Now there's still a current running through the voltmeter, but those current is not detected by the ampermeter, because those instrument is bypassed too. There is a considerable deviation while inspecting devices with a low resistance when using this arrangement of the multimeters. The reason is the inner impedance of the ampermeter, which is low but not zero. The resistance of the ampermeter leads to a voltage drop, which is detected by the voltmeter additionally to the voltage drop at the resistor. We can examine those voltage drop at the ampermeter with the help of multimeter number 3. It is now switched to voltage measurement and connected in parallel to the ampermeter. Those voltage drop has to be subtracted from the value displayed by multimeter number 1, by what the resulting resistance becomes more precise. The voltage drop at the ampermeter is 0.126 volt in relation to the total voltage of 1.15 volt while using a 10 ohm resistor as test device. The ratio is just 0.0013 volt to 10.38 volt while using the 1 megaohm potentiometer. Hence, the voltage drop at the ampermeter can be neglected. While inspecting devices with a low resistance, circuit number 1 is beneficial, while circuit number 2 should be used for measurements at devices with a high resistance. Let's replace the test resistor by multimeter number 3 to detect the inner impedance of those instruments. Firstly, we switch the multimeter to voltage measurement. The inner impedance will be very high, for which reason the test arrangement number 2 is useful. The resulting resistance is approximately 600 kΩ at the 200 mV range and 1 megaohm at all other DC voltage ranges. Now let's switch the multimeter to current measurement and observe the impedance with the help of circuit number 1. The resulting resistance is approximately 1.3 ohm at the 200 mA range, 13 ohm at the 20 mA range, and 100 ohm at the 2 mA range. While switching one multimeter to resistance measurement, we can determine the inner impedance of a second multimeter directly. We get 2.3, 11.2, respectively 101.3 ohm while switched to DC current measurement at the ranges 200, 20 and 2 mA. While switched to voltage functionality, we get approximately 1 megaohm at all ranges. That's a remarkable deviation from the indirect measurement at the 200 mV range. Thus I started another indirect measurement with a voltage of 5.6 volt, with a very similar result. Make suggestions for these curious values. Now that we got to know measurement errors caused by the inner resistance of the multimeters, there is still one question left. How reliable are the values displayed by those instruments? All three multimeters are connected in parallel to a voltage source. The same voltage is attached to the jacks of the voltmeters, hence they should display the same value. As you can see, they don't. The accuracy of these multimeters is given as 0.5% from reading plus minus 2 digits. If a voltage of 10.00 volt is displayed while using the 20 volt range, 0.5% of this value have to be added or subtracted. 0.5% of 10 results in a deviation of plus minus 0.05 volt. 2 digits have to be added to those relative deviation. 1 digit is the lowest decimal place of the currently adjusted range. At the 20 volt range, 1 digit corresponds to 0.01 volt, hence 2 digits correspond to 0.02 volt. Thus, the total deviation is plus minus 0.07 volt. If 10 volts are displayed while using the 600 volt range, the lowest decimal place corresponds to 1 volt. 1 digit is 1 volt, hence we have to consider a deviation of up to 2 volt. From there it is always wise to switch the multimeter to the lowest range possible. As you can see, there are also clear deviations while all three multimeters are connected in series and the same current is running through those chains. You might have noticed that there is an additional symbol displayed at the left side of multimeter number 3. That's an indication that the voltage output of the internal battery is at the lower limit and it should be replaced soon. With the help of a new battery, we can discover the influence of the battery voltage on the displayed values. While the old battery is connected to the multimeter, we can read 11.4 volt. And with the new battery connected to the instrument, the value drops down to just 10.4 volt. By reconnecting the old battery, the value rises up to 11.2 volt with increasing tendency. The remarkable deviation is indeed caused by the different voltage output of the battery. Quality multimeters feature a much better internal voltage regulation, hence the voltage output of the battery is a minor issue. At the low budget instrument used in this video, the values diverge in such a way that they are outside of the given accuracy. There is another decisive reason not to buy a low budget multimeter, namely the build quality. To be able to replace the battery, 2 screws with a plastic thread have to be loosened. After approximately 3 replacements, those threads are ruined and the cover can't be closed properly. Furthermore, the insulation of the jacks cracked during usage. Both defects concern the insulation of the multimeter, and there is danger to life while measuring high voltages. So it is a very good idea to spend some more money and buy an instrument of good build quality. You always get what you pay for. Finally, let's discover the influence of temperature on the displayed values. The cover of the right multimeter has been removed at the backside, and the electronics is heated up to a temperature of 27 degrees by a hairdryer. The voltmeter is connected to a DC voltage source, and the value of 10.47 volt is displayed. As soon as I am switching the hairdryer to a higher power level, temperature increases and the displayed value changes slightly. Even at a temperature rise of 29 degrees, the displayed voltage difference is just about 0.04 volt. The temperature stability of this low-budget instrument is not so bad. You can have a closer look at the recorded values at the project page. That's all about current, voltage and resistance measurement for today. Thanks for watching, and always be careful while measuring high voltages.